Have you ever wondered how our sun, the very source of life on Earth, came into being? We're going to take a journey back in time, around 4.6 billion years ago, when our sun was but a twinkle in the cosmic expanse. In the beginning, there was a giant molecular cloud, a vast, cold region of space filled with gas and dust. It was calm, it was serene, with particles idly floating around. But then, something happened. A disturbance, perhaps caused by a nearby supernova, sent shockwaves through the cloud. These shockwaves started to compress portions of the cloud, causing our sun's birthplace to become denser and denser. As gravity got into the action, it began pulling these particles of dust and gas together. This created a spinning disk of material with a bulge in the middle, known as a protostar. As the protostar continued to gather more and more material, it grew larger and larger, and with this growth came an increase in pressure and temperature. Now, here's where things get really hot. When the pressure and temperature in the core of this protostar got high enough, a process called nuclear fusion was ignited. This is the same process that powers our sun today. In this fiery furnace, hydrogen atoms were pressed together to form helium, releasing a massive amount of energy. This energy exerted an outward pressure, balancing out the inward pull of gravity. This equilibrium marked the birth of a star, our sun. This process of growth and maturation took around 50 million years. But for our sun, it was just the beginning. So next time you look up at the sky on a sunny day, remember this cosmic tale. It's a story of dust and gas, of gravity and pressure, and of birth and life. So that's how our sun, the biggest object in our solar system, was born. The sun's power comes from a process known as nuclear fusion. But what does that mean? Imagine millions of tiny, powerful engines constantly running and producing energy. That's what's happening in the sun's core, the heart of the sun. The fuel for these engines is hydrogen, the most abundant element in the universe. Now, hydrogen in itself isn't an energy source, but when subjected to the intense heat and pressure in the sun's core, we're talking about 15 million degrees Celsius and pressures 200 billion times what we experience on Earth. Something extraordinary happens. Hydrogen atoms, usually content to keep to themselves, are forced together. This fusion, this union of atoms, forms a heavier element, helium. But helium weighs slightly less than the two hydrogen atoms that created it. This tiny amount of lost mass is converted into energy, according to Einstein's famous equation, E equals mc squared. The E stands for energy, m for mass, and c for the speed of light. When you multiply a small amount of mass by the speed of light squared, a very large number, you get an enormous amount of energy. And that's nuclear fusion, the mighty process that powers our sun. Every second, the sun converts about 600 million tons of hydrogen into helium, and in the process, 4 million tons of matter are converted into energy. This energy is so vast that it's equivalent to billions upon billions of nuclear bombs. This energy radiates outwards from the sun's core, eventually reaching the surface, and then hurtles through space as sunlight. About 8 minutes and 20 seconds later, this sunlight arrives on Earth, providing the heat and light necessary for life as we know it. So, the next time you feel the warmth of the sun on your face, remember the incredible process of nuclear fusion happening millions of miles away. The energy produced by the sun through nuclear fusion is what makes life on Earth possible. Our sun is not just a glowing ball of fire. It has mood swings too, which we see as sunspots and solar flares. There's a lot happening on the sun's surface. Among its most noticeable features are sunspots, cooler and darker regions caused by intense magnetic activity. They're like beauty spots on the sun's face, but these aren't just for show. Sunspots are areas where the sun's magnetic field loops up and out of the surface, and they can vary in size and intensity. Sunspots don't just pop up randomly. They follow a cycle, appearing and disappearing approximately every 11 years. This is known as the solar cycle, and it's a bit like the sun's heartbeat, pulsing with magnetic energy. Now, where do solar flares fit into this picture? Well, solar flares are sudden, intense bursts of energy and radiation from the sun's surface. Picture a massive explosion on the sun, releasing more energy than millions of nuclear bombs. These flares are often associated with sunspots, The strong magnetic fields in sunspots can get twisted and tangled, and when they suddenly snap and reconnect, they create these powerful flares. So, how do these solar flares affect us here on Earth? You might think we're too far away to feel the impact, but these flares can actually have significant effects. The radiation from a solar flare can interfere with our radio communications and satellite operations. In fact, a particularly intense solar flare could potentially cause a blackout of radio communications on Earth. But don't worry, our atmosphere and magnetic field do a good job of protecting us from most of the harmful effects. In a nutshell, sunspots and solar flares are two of the many ways the sun interacts with itself and the solar system. They're a testament to the sun's dynamic and ever-changing nature, reminding us that our life-giving star is also a powerful and active celestial body. Sunspots and solar flares are just two of the many fascinating aspects of our sun. The sun's influence extends far beyond just providing light and warmth. It's a cosmic powerhouse, emitting a continuous stream of charged particles known as the solar wind. This solar wind, invisible to the naked eye, travels at incredible speeds, reaching Earth in just a few days. As it interacts with our planet's magnetic field, it can create beautiful natural light shows, known as auroras, that paint the polar skies with vibrant hues of green, red, and blue. But the solar wind does more than just put on a good show. It also plays a crucial role in shaping our planet's magnetosphere, the protective bubble that shields us from harmful cosmic rays. Without this solar wind, our magnetosphere would be drastically different, potentially making Earth a much more hostile place for life as we know it. Now, let's talk about solar irradiance. This is the amount of the sun's energy that reaches Earth's upper atmosphere. It's essentially the fuel for Earth's climate system, driving weather patterns, ocean currents, and the growth of plants. When the sun's output varies, it can influence Earth's climate. For instance, periods of lower solar activity have been linked to cooler global temperatures, while periods of higher activity have been associated with warmer temperatures. But the sun isn't just a weather maker. Its influence extends into our technological world as well. Solar flares, those sudden and intense bursts of energy from the sun's surface, can disrupt radio communications and satellite operations here on Earth. And coronal mass ejections, massive eruptions of plasma and magnetic fields, can potentially cause widespread power outages if they're directed our way. The sun's influence on Earth is far-reaching and complex, affecting everything from our weather to our technology. And as we continue to study and understand our closest star, we can better prepare for its impacts, both the challenges and the opportunities they present. Our understanding of the sun is constantly evolving, thanks to ongoing solar research. Scientists around the globe are tirelessly working, using an array of sophisticated tools and techniques to unravel the mysteries of our life-giving star. One of the pivotal components of this research is the use of solar observatories. Ground-based and space-based observatories, like the Solar Dynamics Observatory and the Parker Solar Probe, provide crucial data about the sun's activity. They help us track solar flares, sunspots, and other phenomena, allowing us to anticipate space weather and understand the sun's effects on our planet's climate. But the study doesn't stop at the sun's surface. Scientists are delving deep into the sun's heart, into its core. Here, they study nearly massless particles called solar neutrinos. These particles, produced by nuclear reactions in the sun's core, zip through matter at nearly the speed of light, making them incredibly challenging to detect. However, catching these elusive particles can offer us a unique window into the sun's internal processes. Detecting solar neutrinos has been a monumental task, but it's one that's already providing valuable insights. Moreover, scientists are also studying solar variability, how the sun's output of energy and radiation fluctuates over time. These variations can significantly influence Earth's climate and weather patterns. Understanding them is crucial not only for predicting weather and climate, but also for planning future space exploration and potential colonization. Solar research is a vast and complex field. It encompasses everything from the study of charged particles to the exploration of immense magnetic fields. It requires the combined efforts of physicists, astronomers, climatologists, and many other scientists. But all this work has one goal: to better understand the sun, the star that makes life on Earth possible. With every new discovery, we come one step closer to fully understanding the sun, our life-giving star.